Hi, this is another very short video just laying out some of the prerequisites for the Math Methods class. This one's about 3D calculus, which there are a lot of prerequisites. Again, I'm creating this video, these set of videos, for the undergraduate's Math Methods and Physics course, which we call Physics 306 at my university, Cal State Dominguez Hills. It's meant to just flip through some of the material you should be familiar with before this course. And I may very quickly cover some of that material again at the beginning of our course. You're responsible for it whether we explicitly cover it or not. I should note that this video may be shorter than the others I made similar to it because it really is more of just a list. And my disclaimer is that this is not an exhaustive list of material that I expect is a prerequisite for this course. So you've taken 3 semesters of calculus and of physics before this, and you saw a lot of the calculus and the physics classes before you got to it in calculus. In fact, by the beginning of second semester of physics, in the order we put things, you run into partial derivatives, which essentially just treat all other variables in a multivariable function like constants. Shortly thereafter, in physics, you ran into what we casually call the del operator in Cartesian coordinates. You run into it first in electrostatics in our order of things, but in calculus you don't run into it until the 3rd semester sometimes. By the way, another name for that symbol, the upside-down triangle there that we often call del, is nabla. I only mention that because you might hear it sometime and you'll wonder what the heck is that if you haven't heard it before. You should have run into 3 different ways to apply this. One called the gradient, where we apply it to a scalar function and get a vector. One called the divergence, where you apply it to a vector function and get a scalar. And another one called the curl, which you apply to a vector function and get a vector. You should have seen all 3 of those in calculus. And in physics, in fact, you may have not known that you ran into the last one, the curl, but you should actually have used those. And in fact, as I said before, the gradient we bring up in 2nd semester before you've seen it in calculus. You should also have seen integration in a multidimensional world, just 3 dimensions, of course, for physics for freshmen. You've integrated scalar functions along paths. In calculus, you did path length calculations. They may not have been your favorite, but they were a thing you should understand and know how to do. You've integrated the dot product of vector functions with a path direction. In fact, you did this in physics very early on when you talked about work done by a force in the 1st semester of physics, before you may have even run into integration in calculus. But then again in our 2nd semester, when you talk about electrostatic potential, in fact, that's a defining relationship to have the integral of the dot product of a vector function with the path direction. You've integrated the cross product of vector functions with path direction again in 2nd semester. The Biot-Savart law had that within it, and you should have seen examples of Biot-Savart law, and if not, I have one done out very explicitly for you, not in this file, but I'll show you where. You should have done integration on more than one dimension. You've integrated scalar functions through volume very early to get mass from the density or charge from the charge density. You've integrated the dot product of vector functions with surfaces in Gauss's law. Now, we generally tried to reduce those to cases where the integral was not hard to do, but in principle you did those before you ran into them in calculus. And then in calculus, you should have run into doing somewhat more rigorous work with that kind of integral. You should have seen other things in calculus class. In fact, you should have seen in 3rd semester calculus a couple of theorems that we will do, so I'm not putting them on the prerequisite list, even though they are in the prerequisite courses. Basically, that's my quick list of things in multidimensional calculus that you really should know before this, and again, some of them I'll talk about again. I mentioned that I have examples. I have 2 related videos that I will link to this YouTube video, but I made both of these for my second semester physics class, the same one that you took if you took it here. In fact, if you took it with me, you may have seen these videos before. One shows the gradient of a function of only distance from the origin. So even though I introduced the gradient with Cartesian coordinates, I did that example for them, and it makes life a lot easier once you know the result of that. And another one called Biot-Savart and a long straight wire, where I actually go through the calculation in great gory detail of applying the Biot-Savart law to a section of straight wire. And when you use the Biot-Savart law instead of other techniques, you actually get a result for a finitely long piece of straight wire with a constant current. So those videos are linked, and if you're in my class, you'll also have access to the PDF of this, and those are active links in there. So that's really all I have to say on this. As I said, it will be very short. I'll see you in class.